Right. So I watched the video from yesterday and I realized that I didn't do a very good job at explaining what we were doing. So we're going to do it again. But this time we're going to do it from scratch. So we're going to start by defining what we're doing and how we're going to do it. So the goal is to swing up this pendulum. We're going to get our trusty Excalibur here. We're going to draw our pendulum. And we're going to talk about how we're going to do it. Nice. And we're going to do everything from scratch, except for the one bit that's about automatic differentiation. And I'll talk about that when we get to it. Okay, so first things first. What do we mean when we talk about swinging this thing up? We have to represent the pendulum over time. And we start at time 0, where it's here, and then eventually has to go here. We're going to represent this. I'm going to get my text here with a series of. Oh, I screwed up the circle, didn't I? You fixed that. Good. We're going to have a series of states and controls, and the states are going to be just like it says here in Wikipedia, the angle of the pendulum, and the control is going to be a little bit of acceleration that pushes the pendulum left or right, so plus or minus, positive or negative. And we're going to start at x0, and we're going to have loads of these states until we get to xn, which is the goal state. And at every x, we're going to have a little bit of control. It's going to push the pendulum, we'll use an arrow, either left or right. So we've got u0, u1, up to n-1, and this corresponds to this one, and then this is our goal. So the question really is, now that we have this framework of states, this is it moving through time, what is in the state? And what's going to be in the state of a pendulum is just this angle theta. This is exactly like you would see it on Wikipedia. You'll have the angle here just corresponding to where it is, and that's the only thing we need. Well, we need the angle and we need its velocity. And this is quite common to represent it like that. So we have the angle and we have how fast it's going, and the u is just going to be one number, and it's going to be just a little bit of acceleration. So the first thing we need to do is we need to take this and we need to figure out how our pendulum moves with time. So broadly speaking, or generally speaking, the rule is that the next state is going to be some function of the current state and the control. So these are our states, the angle and the velocity, and then we have some control as well. Okay, so if we didn't have any control, we would only have this kind of acceleration here. So that is the acceleration due to gravity. So if that was the case, whoops, I'm gonna go here. I could say that x or theta, I'll do it for both. We have the theta and the velocity. So this is our angle, and this is our angle velocity, angular velocity, if we have to be precise, right? Theta, actually let's start with this one, because that one's easier. Theta dot at a plus 1, that is this acceleration here. That's going to be negative g times the sine of the angle. What's the angle? The angle is theta. So this is our acceleration, and then our velocity. I'm sorry. This is our acceleration. This is theta dot squared, is what theta squared. Theta dot. I guess the right way of saying is the derivative of the velocity. So this is our velocity, and we want to talk about our acceleration. So that's a slight mistake there. So we said that the acceleration, we can make it an acceleration is going to be minus g times the sin theta. Then our velocity at I plus 1 is going to be our current velocity plus the time step. We always have a time step between each of these states. Each of these states represents a state in time, and they're all separated. This is the missing bit here. X's are separated by dt and time. So dt can be something like 0.1 seconds, or something very small. So it's a very small time step, and just like our position, or in this case angle, is going to be where we are plus our speed times some time step, you can see the same here. So you can see that we have the current speed plus some little bit the time step times times the acceleration, because that's the acceleration of that's the derivative of this. So we've got this at I plus 1 is equal to this at I plus the dt times a. Actually, we should do this one first. I can talk about that later if we have time, and then we can update. Then we can update our theta I plus 1. This is going to be the theta at I plus our theta dot times dt. You can expand this to get the square of dt here. My music stopped. There we go. We can expand this to get the to get a square here. Like if you expand these, you'll see that dt gets squared here. But even written like this is fine. And the last bit here that's missing is our u, which is just a force pushing it in this way. We are controlling, generally speaking, where we put a bit of force in it. We are controlling the acceleration, which means that we have some sort of force here that also affects our acceleration. So that's our dynamics, and this is really the equations we're going to use to simulate our pendulum. So let's get that written in code. Here I have a simple plot. We're starting kind of from scratch. I did copy the plotting code, and we're going to use my differentiation library called trxdiff from this, and we're going to import the nodes and the tensor objects, and these are going to let us, actually we need the sine as well, don't we? Because here there's a sine. So we're going to import these, and then we're going to use the tensors and the nodes to construct our problem. So first things first, we have a time horizon, which means how many time steps. We're going to set this to 50. And we have dt, which is the difference between time steps. So that setups how long it takes, how long we are going to. Actually, I'm going to set this to 1 e to the minus 2. So this is how many time steps, and this is how much time there's between each time step. So that means total time is t times dt, which we don't actually need for this problem right now. Then we're going to have our start state. So if we go back to our diagram here, we'll see that our state has a theta and a theta dot. Just because of how the framework is implemented, we're going to split this into two nodes. So I'll write this first and then I'll explain it. So we have a node that takes in a tensor, which is 0. So we start at 0 with no velocity. Okay, that is our start state. So now let's talk about tensors and why we need this. So each of the x's, you can visualize this. This will be our x0. Okay, there we. Oh, that is not what I want. Okay, let's try this again, shall we? What? So if I draw it, okay, good. Okay, so that's x0. This is our start state, and we have a u0 as well. And you could think of these as being nodes in a graph where each x0 and u0, so this is my u0, these are actually massive though. Can I make them a bit smaller? Yes, I can. Okay, good. So these two get combined together into the function that we defined above. So I'll say this and that here get combined into f of x0 and u0, and this gives us x of 1. So our function combines, or computes the physics and then gives us the next state. And so we can get rid of this and we can just say these two together with some transformation give us x1. And then we've got our u of 1, and similarly these two get combined to give us x of 2, and so on. So that will be x of 2. Cool. And so on until we get our end state, x of n here. So this thing here. And I'll write a little dot 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 here. Okay. And that is our computational graph. And each of the nodes that we're going to, each of the nodes that I'm about to write are going to be all of these nodes in our graph. Okay, so these are our nodes, and I'm going to define a function that takes in x and u and dt, and this gives us next state given x of t and u of t. Actually, I should say x of t plus 1. Okay, so then we go back to our equations here. Actually, I'm going to copy them and we're going to write them in code. I'll comment them out. Okay, so the first thing to compute is our acceleration, because that's needed for both of them. So we'll create a little temporary variable here called acceleration, which is going to be u minus gravity. Well, we haven't defined gravity, so let's define gravity. We'll break these apart a little bit. And we'll define gravity to be 9.81 approximately. We'll say g times the sine of theta. Well, what's theta? Theta is x of 1. Then we're going to say we're going to have the x of a t plus 1. So we'll call this x nu. Or actually, probably I'll call it theta nu. Theta dot nu is going to be x of oh, this is 0, isn't it? Because it's theta here. X of 0. This is of 1 because we have the dot here, plus dt times acceleration. So actually the equations are in this particular order. And then theta nu is x of 0, that's the theta, plus theta dot nu times dt. And we can return theta, theta nu and theta dot nu, and this is the new state. I'll remove this now. And so then what we can do is we can collect our x's. We'll start at x0, and we can have u's, which currently are empty. And for each step, and I'll say t here, in our time interval, we're going to create a new node for our controls. I'll set them to some number. I'll say this is 5 currently. We'll see what that does in a second. So I'll use a constant, which should be pushing it just in one direction. And then we're going to say x's, add the new element, f of the last one, and their u, and dt. dt is defined up here. Okay, so let's run this and make sure that this runs. Cool. So the next thing we have to do is we're going to have to call forward on the last one, and this will unroll the graph. So this, or unrolls, this computes all of the values for all x's. So it's going to unroll the graph, and it's going to give us the value of x's of -1. I will do this on the states because that's the nodes. Okay, so then you'll see here that there is some angle, these are theta's, and there is some velocity. So because we had some control here, that's 5, we will see that our pendulum has moved a little bit. So we're going to plot this now, and this is my plot. This should work, except I'm not importing matplotlib. I will plot this here. Okay, and this also needs theta's, which I will calculate here. This just means that I need to get the values out of our tensors. So for each x in x's, we'll go 0.val, gives us the actual value. We'll have to unroll this. Cool. And that should not we don't have numpy either. I should probably put these imports at the top as well. Let's do our housekeeping. We'll take these imports as well and stick them at the top as well. Actually, I might just leave these ones here because I will need the other ones for other things, but I won't need these. Okay, cool. So we have an animation. And then we'll see that our pendulum is swinging a little bit to the right, and it's actually accelerating because we're adding some small number to its acceleration at every time step. Cool. So let me change the graphic here. Now we're going to do control, and this is the fun bit. So how do we do control? We actually have all of the things we need to do control. So what we want is for our pendulum to swing all the way up, and it's currently down here. So what we can say is we can take our x and we can compute a loss, and that loss is going to be 0 or small, technically have a local minimum when the pendulum is at the top. So we'll say here loss is minimized when at the top. And this is called a shooting formulation because you are effectively unrolling. It's like shooting a cannon. You're unrolling the whole chain. You get some state, you look at what it is, and then what we're going to do is we're going to go back and we're going to compute all of the gradients of our loss function with respect to each of the controls. So this is where our automatic differentiation framework comes in. It's going to take care of doing that for us, so we don't have to do it. It's going to go back on the graph and give us a gradient. And you'll see here in the code, each of our x's has a little gradient. So what should be our loss function? And I'm going to write this. I'm going to write this here. The simplest way to formulate this is to have some target. In our case, this is going to be upright. So if we start at 0, this is going to be pi to be upright. And then we also want to stop. So we want our velocity to be 0. So I'll write this here. This is top, and this is velocity 0. Okay, so that is our target state. And then we're going to say that our loss function is equal to x minus x target squared times some sort of weight. And we'll get into why we need the weights in a minute. But that is going to be our loss that we minimize at every single time step. So let's code that in. Okay, so we have our states and we're going forward, and now we should get our target first. So we'll get another node here. That's our tensor. It's going to be pi. And then we're going to have some weight, and this is our weight. We're gonna make this 1 into the 3, and we can change what the values are. This will make sense when we start adding some other terms to our loss function. Then we have our loss is qf times our last state minus the target, and I haven't implemented squares, so I'm going to have to do this manually. But these are one-dimensional, so it just works, and that's it. Or maybe it's not. Because this is 0, and I will have to do it for our velocity as well. That wasn't it. velocity needs to be just 0, so there's the target for velocity is just 0, so it's -0, which we could just get rid of the 0, and that gives us the velocity target. Can actually maybe break it down into 2, so that this is a bit easier to read. This is our target. Go up, i.e. pi, and this is our stop, i.e. velocity equals 0. And that's our loss. And we can go forward on our loss as well, and that will give us what our loss is. It's going to be quite big now because we multiplied by 1,000, and we're not at the top. So the next step is to implement a gradient descent. So what we're going to do is we're going to take the gradient, and we're going to use gradient descent to optimize u, which means that u of I should be equal to the current u of I minus some learning rate times the grad, I'll say du of I. So this will be our learning rate, and this is our gradient. And our gradients are already computed by our automatic differentiation library, so we don't have to worry about that. So we just have to do the actual gradient descent loop. There's a couple of things here that we're going to need to do. We need the learning rate. Actually, I'll call this mu. I'll make this small, maybe that. This is our learning rate. And we can tune that as for anything else. We're going to save our losses so that we can actually plot them. And we're going to give us some iterations. I'll go with loads of iterations for these kinds of problems in this formulation. You might need quite a lot. I'll call 0 grad. This 0 is a gradient. So every time we start from 0, it just means that we're not saving some old values that will mess things up. We'll call forward, and then we'll call backward. Actually, we might not even need to call forward here, but I'll call forward anyway. There's a very good chance we don't. Anyway, we'll get some printing. We'll say at I equals I, our loss is the val. So these are all tensors, so I am going to have to index into them, which is why I need to do this. I'll get precision, and then for each u, we're going to do this rule that we just wrote here, and this is basically just gradient descent, vanilla gradient descent. We need to update the value of u, which is dot val. Remember, we have value and gradient. Dot val minus equals, so we do it in place, mu times u dot grad. And if we run this, we get a sec fault. Very likely because I ran this too many times and messed up the computational graph. So let's restart and see if this works. Okay, it is working, but I wanted to say that this is equal to 0. I have so many prints. It's also not optimizing it though. Let's see. For some reason, these are not changing. Oh, and I probably, actually, I'll append my loss. What's the val? Just to save it. But it doesn't seem to be improving at all, which is weird. Now uses an empty array. Well, that's a problem, isn't it? So I need to add my u's to the array of u's. That makes sense. Okay, so now we have both of them. We should be able to crash the kernel. Restart it, no problem. It does sometimes crash when you okay, crash it again. Lovely. Let's see what we've done wrong here. Okay, so we've got x's, we've got u's, we are saving the u's, we're saving the x's. This is fine. So I have a bunch of x's and I have a bunch of u's. These guys, there's a 50 of these and 51 of x's. That makes sense. Make this a bit smaller, huh? Okay, cool. We better get rid of this forward call. Is that messing it up? That was messing it up. Why would that be messing it up? I'm surprised that this forward code was messing it up. I'm gonna try this again. Seems to be calling forward on this, and then calling forward on the loss is sec faulting it. Well, we don't need this anyway. Calling forward on the loss will call forward on the axis as well. And I've just crashed it. We'll reload. This is a problem with VS Code's server. I should really probably use something else. It is quite prone to crashing, which is quite annoying sometimes. Anyway, okay, so now we have it optimizing. I have a feeling my learning rate is a bit too low, so maybe I make this a bit higher. I actually reinitialize it to see if that's the case. Cool. Okay, so now this is going all the way down, and we'll do some plotting. We'll get 2 plots. Yeah, where we're going to plot. Let's see, 10.5 maybe. That's all right. So left, we'll have the theta and theta dot, and right, we'll have our controls. Okay, so let's see. I need to save these. I think this is our axis object. Yeah, okay. So here we're going to plot for each time step x's of 0 dot val, or rather x of 0 dot val for x in x's, and that's going to be our t plus 1, of course, because we have t plus 1 states, and we're going to plot our velocities as well. That's nice. We'll get grid. That's cool. Why does this feel like that feels nicer? Maybe the spacing in between, even though 5 is 2 times 5 is 10. We'll go x label, set x label time, step. Well, time is fine. In seconds, and the y label is technically degrees, or degrees per second, because like this, because our theta is so this is our theta, and this is our theta dot, so this is our angle, and this is our velocity, and we just need to get our legends up. Cool. And that is our state, and now we'll just copy this, and we will have our controls. So this is control, and this is going to be u and not x's, and then this is effectively force, so force is newtons, right? And I need to change the axis and make sure that we are t and not t plus 1. Node object is not subscriptable. Because we only have one u, so like this. Cool, and so that is our control. And if we, maybe I should have actually copied this and pasted in here. And if we run our plot, we'll see that our pendulum now goes from the bottom to the top. Hopefully. I'm hoping. Yeah, cool. Okay, so now it goes all the way to the top. So now we'll call this success. And I'm going to change the title, because now we're going to do constraints, or rather u costs, because I'm not necessarily going to do constraints. Well, I will a little bit. Okay, so we successfully made our pendulum swing to the top, which is very, very cool. But now we want to explore what happens. Okay, so we'll go here. What happens if you don't have unlimited force? So as you see here, I'll copy this figure. I think I can just copy it and paste it here. Nice. Okay, so this is our figure. This is our figure here. This is unlimited force to swing. So it's going from minus 80 to from plus 80 to minus 80, and it's swinging the pendulum up. Fine, but we don't always have that much force, indeed. So let's see what happens when we don't have unlimited force, or rather, what if you don't have unlimited force? And what we're going to do is, well, we're going to do a couple of things. Number one, I'll go here. We're going to enforce limits on u. And we're going to do this by adding things to the cost function, to the loss. And this is known as soft limits because, well, as we'll see, the gradient descent algorithm doesn't really have to respect these. And two, we're going to add a general cost on u, and we'll give it more time so that it actually learns how to swing to the left and right and build up momentum. But first we're going to do the first one. And for that, we're going to, let's do number one here. We're going to take our loss, and to our loss, we're going to add, well, before we do that, we're going to set some limit to our u's, and I'm going to set it to something smaller than this. So this is 80, I'll set it to 50, just for now. And we're going to want to basically say, if for each u, for each I, really, if u of I is less than minus 50 or u of I is greater than 50, then loss. Otherwise, okay, or 0, aka 0. The way we're going to do this, and I'm gonna put it here, is we're going to use a rectified linear unit. So we're going to here and we'll go relu. That's not the right relu. Rectified linear unit. Cool. So this is a rectified linear unit, and it is 0 when the variable is less than 0, and the actual value of the variable otherwise, also known as max of 0 and the variable. Very useful for neural networks and very useful for us. So max, if you look at it long enough, you can convince yourself the max of 0 and, well, let's formulate it first. Max of 0 in a number is going to be either 0 or that number. And so we don't care if it's positive or negative, so we're going to square u. But we don't just want to square u, we want u squared to be within the limits, and u squared is within the limits when u squared is within u limit squared. So u is between minus 50 and 50, and u squared should be between minus 250 and 250, or because it's positive, between 0 and 250. And so this this function here, also known as relu, equals, so this is relu here, will be 0 if u squared within 0 to 250, otherwise will not be 0. And so we'll add this for every u and see what our optimizer does. So that's the first step. So let's do this. This is our loss here, and for each, this is going to be our control cost. For each u to our loss, we're going to add, actually first things first, we need to import the relu function from our automatic differentiation framework, and we'll add the relu of u times u minus the limit. So let's have the limit here, we said it was 50, minus u lim squared. And I'll multiply this by a small number, just so that, because it's summed over 50 time steps, I don't want it to blow up as a number. And we'll run this. I need to import this. Actually, I will restart this. Okay, and rerun this. And now we'll let the optimizer run again. And you'll see here that it might get to 0. It should get to 0 eventually, but you'll see here that our u's are now bounded here at 50 and minus 50. So it's learned to respect the limits that we gave it. We have it at, I'm going to copy the image. Actually, first we'll verify visually that our pendulum is swinging. Quite important. Okay, so it's still swinging up. It might be a little further away. We can solve this by running it for a few more iterations until it actually gets to 0. It might take it quite a while. You see here it struggles. We could implement better algorithms so that it converges better. But still, it's just going to give it a bit more time and get a bit closer to 0. For our comparison, this is our version with limits. So this should be a bit closer. It's a bit closer. We'll copy this and we'll put it in on our whiteboard. And this is what happens when you give it. That's not what I want to do. Here. So this is what happens when you give it control limits. That's our idea 1. And then this is our idea 2. We're going to give it a general cost on u. And I'll tell you what I mean for that. That just means we're not going to give it a specific limit. We're just going to add u squared times a small number. So very, very similar to this, where we're squaring it so that the positive, I should say, for each u, for each I, u of I squared. So this is very, very similar to this, except we're not bounding it anywhere. We're just giving it a generic cost. But before we do this, let's say we'll call this 1.5. What if very small limit? And I'll show you what it means by that. This is where it's going to break. So we're going to go here, and we're going to set the limit to 10, which is not enough for it to actually swing the pendulum, or shouldn't be enough. And you'll see that it's going to get stuck. It's not going to be able to do it. And you see here that it broke. It isn't respecting the fact that our limits are 10. Like, it's trying, but it's not really getting it because our limits are a bit too conservative. Now, if we gave it more time, so see, it's the cost term to be at the top is overpowering, and our optimization is quite broken. We're going to add this here as our as a 1.5 on our whiteboard. Okay, so we started with unbounded, unlimited force. I can go up, I can push as hard as I can, I go up. We added some limits, and our limits are not as restrictive. We can follow them, they're 50, and we can still do the same thing. So you still see here that these two are very, very similar looking, where we just go left and go to the top, and then we make it very small, and that really breaks it. So now we're going to fix that. So instead of doing this, what we're going to do is we're going to give it a bit more time. So we're going to say this is 100 time steps instead of 50. And then step 2 is we're going to get rid of this ReLU, and instead we're going to add just u squared. So use as little energy as possible, but now you have more time. So let's see what happens when we do this. And we're going to run this. And this should take a second. And we should see it. Let's run this. I have a feeling that we might need to give it a bit more time, actually, which we can do. Yeah, we might need to give it a bit more time, or I might need to give it a bit more of a control cost. This is also possible. Let's try this. Try and get this to work. Okay. I'm gonna play with this for a sec. So basically I'm trying to get it to swing up, and it needs to have enough time. It needs to have enough time to do it, and it needs to have a reason to do it. And the reason is cool. Maybe this is too much time, actually. Possible. Let's see. Yeah, okay. So it needs to have enough time and a reason to actually swing the pendulum. Let's see if this works. I feel like this is too much time, though. Should be able to get it with a little bit less time. Cool. There's a lot of time steps here. Still somehow managing to swing the thing without using the Maybe if I penalize it a bit more. Okay. I'm wondering if it's still managing to swing it in the time steps. Okay. Of course, I can penalize it more. Oh. I crashed everything again. It's always a fight between trying to get to the top, which is one of our cost terms, and trying to swing the pendulum. Okay, let me double the horizon then, because I feel like, ooh, that's definitely not good. Let's try this again. Okay, so this is now hopefully enough time for it to be able to do it. Okay. Ah, cool. So there we go. Given enough time, took me a minute to work it out. Actually, maybe I should plot also our axis, our losses, I mean. So, well, n. These are our losses. This is our loss function, which is going down. See here, it's swinging the pendulum left and right when it gets to the top. Took us a second to get there, but we needed to give it enough time and a reason to do it. Okay, so this is going to swing left and right a bunch of times, and then it's going to go to the top. Okay, so here we go. Swing, swing, we pick up momentum, and eventually it's going to go to the top. So it's not quite at the angle, so we can actually make it, make this a bit bigger to, you know, drive it a bit closer to the top. So we're going to do that now. Ooh, and that explodes. So as you make the losses bigger, you might need to take smaller steps. Even smaller than that, I guess. That is quite funny. Or maybe that's just too big and needs to be a bit smaller. Okay, hopefully. There we go. Okay, that's nicer. Okay, so now, hopefully with enough iterations, it's going to converge quite close to the... I'm actually going to run this a bunch more times, see if it's really converged. So here it is really converging. We could run this for longer. See if this gives us a better animation. Meanwhile, we'll copy this image and we'll put this here as our last thing, which is we give it a general cost and enough time to swing, and then it should be able to just do a couple of swings left and right until it gets enough momentum to go to the top. Okay, so this is a bit nicer. It picks up momentum, and eventually goes to the top. Then you see here it's actually not using that much control, that much force compared to before. And so the last question here, and I'm gonna put it in here. We'll call it, update the labels here. We'll call it left or right swing, question mark. And so the thing is, left or right swing. Currently it's swinging to the left first, and you'll see here it's going to go this, sorry, to left first, and then it goes to the right. And can we reverse that direction? And the reason that it's doing that is because this thing is one way around. So if I put a minus sign here, then it'll change the derivatives of it, and it should swing the other way around. So let's give this a go and see if we can replicate it. So see here, we've managed to invert it, and it's swinging the other way around. And we'll plot that as well, so that we can see the result of that. I'm gonna copy this and put it to a whiteboard as well. So here's the whiteboard. This is using target negative pi will mean swinging in the other direction. So we go to our whiteboard here. We started with unlimited force, then we had some control limit, we broke it, we gave it enough time to swing, and then we inverted the cost so that we see the swing up in the other direction. So that should go right, And, well, I think it has a bit too much time, to be honest with you. It goes up that way. Okay, actually, I might have a bit too much time. I'm gonna only give it 50 time steps, just to see if we can. Yeah, that's a lot nicer, isn't it? Should still see a swing up, but now we see a few less iterations. So okay, so then the next thing is, can we do better than this? Now the reason this is happening here is because target minus pi and pi minus target, right? Or target, yeah, target minus pi or target minus minus pi, effectively. So here we've got minus pi minus minus pi will give us two different gradients. So as we go here, where we did the updates, we're going to change the signs of the gradient one way or another. And yes, we can do better. And this is the last thing we're going to do. We'll call this number 3, using a cosine cost. And so cosine of 0 is going to be equal to 1, and cosine of pi over 2 is 0, and cosine of pi is also 1. So we can make, because our target is pi, the same for cosine of negative pi, we can check these things. Cosine of pi is the same, sorry, negative 1 as the cosine of np pi. So this is negative 1. And we can make our loss be cosine of theta plus 1 and minimize this. And this is going to have 2 minimum. So I'll write this down here. 2 minima, 1 at theta equals 0, and then 1 at theta equals pi. So this means if we start at 0, 0, 0, 0, 0, we won't see any, we won't be able, or we won't have gradients. This is my claim, and now I will demonstrate this claim. So let's start at 0, 0. So we reset everything to 0, like the values of u is 0 here, and then we'll change this. We'll use again QF 1 plus cosine of the angle here, and I need to import cosine as well from our trusty automatic differentiation library that only sometimes seg faults and crashes. I think this has to be a float. Maybe I only implemented a right side. Okay, I only implemented a right side addition. Okay, so now as I showed you, nothing's happening here. The reason nothing is happening because the gradient is 0, because we are at a minimum. However, and this is what we're going to do, we're going to show effects of warm starting. So we'll say u equals to 2 and u equals to minus 2. I claim will change swing up direction. So we can have left or right without editing our costs by starting at different controls. And the reason why I claim, oh, don't know what happened there. The reason why I claim this is because plus is going to swing this way and minus is going to swing this way. And I also claim that this will be opposite of the direction, which I'm not very sure about. So I also claim, that's my maybe claim, it's opposite to eventual direction, or like to swing of direction. Because we start this way and eventually we go up the other way. So I'm thinking this is going to be opposite. So I'll start it, I'll seed it here, and I'll say minus 2. And we'll run our trusty optimizer again. Here you see that, ooh, that cost has gone up quite a bit, hasn't it? I think we might need a different learning rate, actually, because this feels, well, I think for demonstration purposes, okay, but I will change the learning rate. Okay, so now we've gone left, and I said that u is minus 2. Okay, so maybe claim this is not true. But let's see if the other claim is true. Let's say I make it to 2. So we went left one time, and now let's see if we go the other way. So now this should go the other way. So to the right, depending on the seating. Okay, so now we go to the right. So these are the two different directions. So depending on how you seed it, it will have an effect. So this is u equals 2. I will put this here. U equals 2 to start with, and then I will have them both so that we can see them. I'll have -2 as well here and run this again just to demonstrate that point as well, and that should be the other way around, and that indeed is the other way around. So we'll take this and put this here. Cool. And that is the effects of warm starting on the pendulum. I think that really is it. We've gone from definition to physics, computing the physics, to making our optimal control problem, writing our losses, writing our gradients, and then having a look at what the different formulations, what effect they have on our pendulum controller. So hopefully that was a bit easier to follow than the last one. And yeah,